Hey everyone, my name is Remi. I'm a research scientist at the MIT Plasma Science and Fusion Center. Thank you very much for having me. It's a great opportunity to go back to my home country. Today I'm going to talk about FESTIM 2, which is the upgraded FESTIM. We didn't call it FESTIMX. We should have maybe, but we were a bit boring. We just called it FESTIM 2. But it's basically the upgrade from legacy FEniCS to FEniCSx. I'm just going to give a 1-2-minute crash course on nuclear fusion, which is what we're trying to do. So nuclear fusion is the opposite of nuclear fission, where we try to, in nuclear fusion, we try to break a big atom into smaller atoms. Fusion is doing the opposite. It's taking two light elements, so hydrogen, so namely deuterium and tritium, which are like two isotopes, so different flavors of hydrogen, fuse them together, produce helium and an extra neutron, and then we have the infamous E is equal to mc squared equation. That reaction releases a lot of energy. That's fusion in a nutshell. Now, zooming in on this little guy over there, the tritium. Tritium is radioactive, and it poses a bunch of concerns in terms of safety. More generally, hydrogen poses issues in terms of hydrogen embrittlement. Hydrogen is very small, and we'll talk about that, so it can penetrate everywhere. So our research group is focusing on the fuel for fusion. So please don't ask me questions about complex plasma physics or stuff like this. This is not what we're doing. What we call the tritium issue is that you have a fuel cycle in a fusion reactor, where basically the fuel and the impurities are flowing from one component to another. So you have I won't use that. You have the plasma, so the core reactor on the left. You have to inject fuel, but you also have to breed your own fuel. I won't go into details. Happy to talk about that in the break. But basically, you have hydrogen and sometimes radioactive hydrogen flowing everywhere in your system. And so we need to be able to track it. We need to be able to simulate where it goes, how much is retained in components. In order to design components, we need to also be able to predict throughput for fuel. Zooming in even more, if we look at the metal lattice, hydrogen is so small that it can basically penetrate the metal lattice. So here we have a very simplified view of what can happen. So you can have, I'm going to risk it. Okay. So you may have hydrogen that is directly implanted in the lattice, then diffuse, so it jumps from one interstitial site to another. Eventually, if you have defects like a vacancy or an impurity or grain boundaries or stuff like that, hydrogen can be trapped. So it will sit there nicely because it has a sort of like minimum of potential energy. And so that poses some issues. If its energy is high enough, it may detrap, start diffusing again. You may have some damage caused by the implantation. You have some fancy surface effects where you may have molecular recombination, and all of that gets more complicated if you have several species, several isotopes of hydrogen diffusing at the same time. So we have equations to predict all these processes. I'm going to give the very simple version. It's basically diffusion reaction. So we can treat the diffusion of hydrogen with a simple Poisson equation. Sometimes we have some fancy non-Fickian diffusion. In the previous talk, we saw the potential-assisted, electrical potential-assisted diffusion. Sometimes we have temperature-assisted diffusion. I haven't put these terms here. But then all the trapping and detrapping and interactions with other species, they basically take into account as reactions. So I put one reaction here, which is the trapping reaction. So we have Cm, which is the mobile population of hydrogen. We have Cti, which is the concentration of trapped hydrogen in defect I. And so we have, it's like a prey-predator model, basically. We have a trapping rate and a detrapping rate. And so what FESTIM simulates is basically this. So here we have a component of a reactor that is exposed to hydrogen, to tritium specifically, and it's implanted from the top. Here you have a cooling pipe, and you see hydrogen diffusing. You have some fancy stuff going on in the interface, and I'll talk about it in a minute. But basically here what we're looking at is potentially how much tritium will go into the cooling water, because that's contamination. At the interface, this is where things get a bit funky. We don't have, like you would have in a heat transfer problem, we don't have continuity of solution of the solution C. We have continuity of what we call chemical potential. So we have, obviously, we have flux continuity, but depending on the material, we may have this equation here at the interface. So C over the solubility is equal to C over the solubility on the other side. So if you have two different materials with different solubilities, that will induce a jump, a discontinuity in concentration. This is quite tricky to do, but sometimes you have this equation, which is very tricky to do, and this is what I'll try to talk about today. Just a word about FESTIM. So yeah, previously it was on legacy FEniCS. Now it's on FEniCS. There's a lot many new features that we added thanks to that, but I'll focus on the interface. A few examples of what we do with FESTIM. So designing components, predicting tritium retention in a reactor. In the middle are two experiments that we have at MIT that we validate FESTIM with. On the right is data analysis for hydrogen experiments. I'm not the only one doing this work. Really want to give a shout out to Jorgen and Joe from the FEniCS team, who've really been instrumental in this work. Yeah, FESTIM is used everywhere. Great. I just want to point your attention that most of our users are the fusion community and also the fusion research organizations. This is very important because if you remember yesterday we had this comparison of the engineer versus the FEniCS developer. Well, we have a different view of you guys. We see you guys as math gurus who know how to code and how to read math. Whereas the people we're trying to appeal to, they're not necessarily FEM experts. They don't necessarily know how to program. So we try to really make FESTIM as simple as possible. So this is what a typical FESTIM script will look like. We start by initiating a problem, and you won't see any FEniCS code in there. That's very abstract. We define a mesh. We define materials. We define subdomains. Eventually species. So here it's very simple. You have only one diffusing species. Temperature, boundary conditions, very abstracted. Some settings, step size. Some exports, initialize the model, run, and boom, that's it. You have a FESTIM simulation. So it's very different from the other packages we may have seen so far. Before FEniCS, to deal with it, before FEniCSx, sorry, to deal with this interface condition, we used what we call the change of variable method, where we introduced this variable theta, and we basically rescaled the whole problem from it. So this discontinuity turns into something that's continuous, so it's very nice. And we now have to rewrite all these equations for theta. And that in the past caused some issues. It made the implementation a bit more complex. It was mathematically correct, but it made the implementation a bit more complex, and sometimes we had performance issues as well. With FEniCSx, we can use the mixed formulation or mixed domain approach. I've heard different things, which is very nice. So basically, you have your mesh, you split it in two submeshes, and you will solve the bulk equation on each of these subdomains, and then have an interface condition to basically stitch it back together. So yeah, so that's where at the interface we have a DG method to enforce this discontinuity. We have several ways of doing it. One with a very simple penalty. And the other one is the niche method. I didn't come up with these, so if you have any questions, please redirect. Jorgen is both a very clever math person, a very clever programmer, but this is a picture of him when he visited me at MIT in front of a mock-up of a tokamak, so he also knows about fusion, so really Jorgen's your guy. Anyway. You end up with your concentrations on both subdomains, and overall you have your nice discontinuity. So it's nice because we don't need the change variable, but it requires a penalty. So it's another magic wand that our users need to understand. When it's too high, then your problem doesn't converge. When it's too low, it converges towards the wrong solution. So that's the drawback that we have to deal with. However, using that provides a lot more flexibility for new interface physics. So we can play with different interface conditions. We have a lot more control on what equation we can put there. So that's something we're really looking forward to. And it provided a nice boost in performance. So that's FESTIM 1 with the change variable method, and that's with FESTIM 2 with FEniCS looking at. We also implemented a change variable method to be able to compare apples to apples. I'm running out of time, and that's the multiphysics part. So I think I'll stop here. That's a nice visualization of a heat exchanger where we simulate tritium contamination. And on the horizon, there's very cool things that we have now in FEniCS 0.11 that we are exciting to test. One is the real element, because that's what we need to be able to simulate gas enclosures, codimensional meshes, being able to couple a 1D mesh with a 2D mesh that would be useful to simulate diffusion across grain boundaries, for example, all of that. So we need to do a bit of work to upgrade FESTIM to 0.11, but surely we'll start that when we're back in Boston. Thank you very much, and if you have any questions, don't hesitate.
Thank you. Any questions? Yeah?
Just out of curiosity, this interface condition, couldn't we also introduce a Lagrange multiplier on this 2D mesh?
Yes, and this is something we've talked about. I got to learn about Lagrange multipliers. I was very happy about that. It's something we talked about. I believe you have Jorgen, you have a demo somewhere. And it would be about finding time and people that know what they're doing to implement it. But yeah, that would be a third method that we could use.
For FSI, so if you're interested,
That'd be great. Yeah, we should catch up. Yeah.
Great. Any more? Yeah, Jack, please.
Yeah, you mentioned coupling at the end. You had this kind of like grand scheme, and I was wondering why you decided to maybe couple different codes together rather than kind of consolidating on top of it.
It's a good question. I think James, you might talk a bit more about multiphysics, but basically the physics that we need to couple, sometimes they're not like, for example, we need neutronics. Neutronics are the solving how the neutrons are transported in matter, and for that type of physics, it's typically a Monte Carlo code. So it's hard to just add that, and it's very, very complex. I would rather leverage something that already exists. And for CFD, which is very important for this, we're not CFD engineers. So it would be very hard for us to make a model that's as good as existing like leading software like OpenFOAM or Star CCM, stuff like that. So we would rather use what already exists and work on the interoperability.
Any more questions? Yep.
So these jump conditions are sometimes a bit better enforced if you change the discretization in terms of the finite elements, right? So what kind of elements are you using?
So we use, when on both, typically, we're a bit boring, we use CG1. I know. We have CG1 elements on both submeshes. And it's basically the jump is enforced between external facets. That's one of the.
The other approach is to go with the H-diff conforming elements, like Thomas, and that gives you this continuity in the values, but the continuity in the fluxes.
The H conforming elements. You see, I don't know what these are, but but we should talk.
Great. For the break, yeah, please.
It does. It's a bit more finicky because basically you need to scale your equation differently based on where you are in the domain. So you have two types of materials that have different solubility laws. One gives this, and when you have dissimilar materials, it leads to this nonlinear interface equation. So it's possible. That's the situations where FESTIM 1 really the change variable really didn't work well in FESTIM 1. When you had these, it's possible, but you have to introduce either a square root in your formulation, which is nice, or have everything squared, which is nice either. So it wasn't very stable.
I saw, yeah.
Yeah. Thank you for the great presentation. You said that you could do multi-species chemical reaction.
Yes.
You wrote it somewhere in your presentation. And I was wondering also if you had more complex diffusion law.
Mhm.
You said you were solving thick kind of model of diffusion. But
Yep.
do you have something that can take into account when you have multiple species for diffusion like
Yeah, so you can have an arbitrary number of diffusing species in FESTIM 2. That wasn't possible in FESTIM 1. It's something that we've added in FESTIM 2. In terms of diffusion models, FESTIM 1 had fixed diffusion and also like the Sorey effect. It's also called thermophoresis or temperature-assisted diffusion. That was present in FESTIM 1. We didn't find a nice way to add a better. It was added in a bit of a hacky way in FESTIM 1, and we didn't find yet a nice way to add in FESTIM 2 because this is not a model that we use for our work. We're waiting for someone from the community to really nag us about it to start working on it. But we know the equations. We know how to implement it. Yeah.
Great, lots of discussion. So much to do in the break. So let's thank the speaker.
Thank you very much.